Section 4.3, the addition rule of probability. In the previous section we talked about events. We're going to break that down a little more and just call a compound event any event combining two or more simple events. So in other words, we have simple events and compound events. As an example, suppose we roll a pair of dice. If we let A be the event that the dice add up to 8, and let B be the event that one of the dice is 5, we can find the probability that A happens or B happens or both. And we write this as probability of A or B, as in this first case. We also sometimes use symbols, which you'll see occasionally in the homework, but this just means the probability that A happens or B happens. Technically, this symbol here is the union symbol. Here's an example. So we want to find the probability of picking a subject who lied or who the polygraph says lied. So if we break this table down here, the first row are the people who this polygraph test says they lied. In the second row, the polygraph said these people did not lie. Now, whether or not they actually lied is given to us by the columns. So in the first column, we have the people who did not actually lie, 15 and 32. And in the second column, we have the people who actually did lie, 42 and 9. So for example, these 15 people, they did not lie. However, the polygraph said they did lie. That's a false positive. And here, the 9 people here, these 9 people did lie, but the polygraph said they didn't lie. That's what we call a false negative. So if we want to find the probability of picking a subject who lied or who the polygraph says they lied, we need to label our events first. So I'm going to call the event where the polygraph says they lied, event B, and the event of picking a subject who lied, we're going to call A. So let's first look at how many people the polygraph said lied. Well, all we need to do is add up the total number of people in the first row, and we get 57. Next, let's add up the people in the column did actually lie. 42 and 9 give us 51. So the 57 are the people who would be in the B event, and the 51 people would be in the A event. Now let me add up the rest of these columns just for the sake of completeness, but also it'll help calculate how many people were surveyed altogether. For example, if I want to know how many people are in here, I can just add up the two rows of people, meaning I can add up 57 and 41, or I could add up the two columns of people, 47 and 58. In either case, we're going to get 98 people surveyed. So it's tempting to try to say that the probability of A or B, in terms of a classical approach to probability, would just be to calculate the simple events in event A and divide it by the total simple events in our sample space, and add that to the simple events that make up B divided by the total number of simple events in our sample space. If we did this, we would get 51 out of 98 plus 57 out of 98. The problem here, if you actually add those up, you'll get a probability that's greater than 1. But of course, we saw in the last section, we can't have a probability that's greater than 1. So we've done something, or there's something a little more to this. So we need to be careful. And basically what's going on is we've double counted the 42 people who did actually lie, because we counted them in our 57, and we also counted them in our 51. So when we try to add these together, we've got 42 double counting in both of them. So let's come back to this in a second and look at, after we look at the addition rule for probability. So when you're trying to find the probability of an event A or B happening, you add up the probability of A happening plus the probability that B happens and subtract off the probability that they're both happening. In other words, we have to subtract off one of the places where we double count. Symbols, we talked about the union symbol here, meaning or. But we also have the upside down version, which we'll take to mean and. Technically, this symbol is called the intersection. So the definition that we want to talk about first is when A and B are disjoint. That is, if they cannot occur at the same time. So in other words, if A and B cannot occur at the same time. If that's the case, then the probability, so if two events are disjoint, the probability of A and B occurring is 0, because they cannot both occur at the same time if they're disjoint. Now use what we know about the addition rule for probability. We have the probability that A or B happens equals the probability of A plus the probability of B minus the probability that they both happen. So the probability that A happens is 51 over 98. Why? Because 51 people actually lied, so that's our numerator. That's the total number of ways we could pick somebody who actually lied, divided by the total number of people in our survey. This is the classical approach to probability. Now the probability that B happens will be similar. B is the polygraph says they lied, so the probability will be the number of people who the polygraph said they lied divided by the total number of people in our survey. So the probability that B happens is 57 divided by 98. Now we want to subtract off the probability that they both happen. In other words, the probability that a subject lied and also the polygraph says they lied. So that'll be the 42 here, because these people actually lied and the polygraph said they lied. We also wanted to find the probability, we also want to divide this by 98 because there are 98 people in our survey. So that would be 42 divided by 98. Now if I combine all these together, we'll get 66 divided by 98, and plugging that into our calculator gets us approximately 0.6735 probability that A happens or B happens or both. Another example. Suppose we roll 2 die. We let A be the event that we roll a total sum of 8, and we let B be the event that one of the dice is 1. Find the probability that A happens or B happens. We'll use our addition rule again, and let's look at the sample space for rolling 2 dice as we did in the previous section. Now we know the addition rule tells us that we want to find the probability that A happens. In other words, the probability that that we roll a total sum of 8. So to do that, we look at, in our sample space, look at all the simple events, count up all the simple events that would give us 8. So that'll be 6, 2, meaning we roll a 6 on the first die, a 2 on the second, 5, 3, 4, 4, 3, 5, 2, 6. So the probability that we'd roll a total sum of 8 would be those 5 simple events divided by the 36 simple events in our sample space. Now we want to find the probability of B, the event that one of the dice is 1. So the first thing we look at is what happens if the first die is 1. That'll be our first row in our sample space. But also, it could happen that the second die is 1, which is the first column in our sample space. Now we want to be sure that we don't double count the 1, 1 where they both happen. So there are 11 simple events in our sample space that would give us a 1 on either die. So that probability that B occurs would be 11 divided by 36. Now think about the probability that A and B both happen. In other words, we roll a 1 on one of the die and we get an 8. But if you notice, there's no way for that to happen. There's no way we can get a 1 on one of the die and also roll an 8. So the probability that A and B both happen is 0. In other words, the events A and B are disjoint. So adding all these up, we'll get 16 divided by 36. Throwing that into the calculator gets us 0.4444. So let's review disjoint events. Going through a couple examples really quick. Check to see if these two events are disjoint. Event A would be arriving late for your next class, and event B would be arriving early for your next class. Since there's no way to arrive late for your next class and arrive early for your next class, these two events would be disjoint. How about randomly selecting a drug screening result and getting one that is a false positive, and randomly selecting a drug screening result and getting one from someone who does not use drugs? These would not be disjoint. In other words, it is possible for both of these events to occur at the same time, because a false positive would be somebody who doesn't use drugs but got a positive drug test result. And event B is someone who does not use drugs. So somebody who does not use drugs could fall into either one of those categories, meaning either one of these events could happen, both of these events could happen at the same time. All right, last one. Suppose your refrigerator doesn't work. That's event A, and event B would be your television doesn't work. Are these events disjoint? And this one's tricky. The answer is that they're not disjoint, although they seem like they would be. However, one possibility is that your electricity has gone out, in which case your refrigerator wouldn't work and your television would work. Another way to think about disjoint events in the addition rule is to think in terms of Venn diagrams. So if we consider this blue circle to be the probability of some event A occurring, and the red circle being the probability of some event B occurring, they're disjoint if there's no overlap between the probability of those events occurring. If we instead look at them where one is overlapping the other, then the events are no longer disjoint. And this area where they overlap is what we call the probability of A and B occurring. In other words, where they intersect. If they're disjoint, then the probability of A and B occurring is 0. In other words, the probability that we're in the blue circle and in the red circle is disjoint. We can't be in both of them. In which case, when we try to calculate the probability of A or B occurring, and we have to subtract off the probability of A and B occurring, when they're disjoint, there's nothing to subtract off, because there is no probability, there's no way to be in both event A and event B, so the probability that you're in both is 0. So that goes away, and then when we're talking about disjoint events, the probability of A or B occurring is simply the probability of A plus the probability of B. One note about complementary events: the probability of A union the probability of A complement, or in other words, the probability that A occurs or the A complement occurs, is the probability that A occurs plus the probability that A complement occurs minus the probability that A and A complement occur. So recall that A complement just means A does not occur. And if you think about this, what could the probability that A occurs and A does not occur be? But of course, that has to be 0. So we get rid of the probability that A occurs and A does not occur, and we simply have to add up the probability that A occurs plus the probability that A does not occur. But of course, if you're looking at the probability that something happens and the probability that something does not happen, those surely have to add up to be 1, because either an event happens or it does not happen. A little algebra would show that if we subtract probability of A from both sides, then we get that the probability that A does not occur is 1 minus the probability that A occurs. And vice versa, if we subtract off the probability that A does not occur from the left side, we'll get that the probability that A occurs is 1 minus the probability that A does not occur. As an example, suppose a study finds that 57% of people between the ages of 18 and 25 prefer Coke to Pepsi. What is the probability of randomly selecting an 18 to 25-year-old who prefers Pepsi to Coke? Well, if 57% prefer Coke to Pepsi, 1 minus 57%, or in other words, 1 minus 0.57, would be 0.43 or 43%. So the probability of randomly selecting an 18 to 25-year-old who prefers Pepsi to Coke is 0.43.